going to let you take over and carry on with Danny, and we'll see you in 50 minutes.
Excellent. Excellent.
Have
Thank you,
fun.
Judy. We will. We're all going to have fun. And a quick reminder to everybody out there, if you do have a question, you're welcome to put it in the chat section. And as time arises, we'll hit Danny with it. Of course, Danny, if you recall from last year, the first EPARTRADE Industry Week, one of the best presentations, we got very deeply into the ChassisSim technology. And it was there that I learned a little bit about you and your career. And I went back and saw some of the books that you've written, and you have genuinely devoted a lifetime of energy to this. And now ChassisSim, in many ways, the culmination. I'm very excited to see what we're going to learn here today.
Excellent, excellent. Well, Joe, thank you very much. Well, and also too, thanks again to Francis for that rather praiseworthy and eloquent introduction. For a split second, I almost forgot who you were talking about. But okay, guys, so what we're going to talk about today, so let me just share my screen, so stand by. I'm also going to share sound as well, because I've got some videos to share with you all. So we've got that. Can everyone see my screen?
I can see it. I don't know.
Okay, cool.
Else, but I've got it.
All right, awesome. Also too, guys, just a little bit of admin here. Because of where my webcam is and where my monitor is located, from time to time, you might see me go up like this. Don't take it personally. I'm not trying to be an uber nerd. It's just where the screen is located. So we put that under vexatious IT issues. All right, no worries. Okay, so are we all good to go? Is everyone set? We're all good. Everyone, can everyone hear me? Can everyone see the screen?
I am ready to roll, and our panelists in the chat section appear to be ready.
Okay, perfect. Well, ladies and gentlemen, welcome to this this ChassisSim presentation for EPARTRADE, and it's such a thrill and such a privilege to be back with you again this year. So, what we're going to talk about today is probably one of the most looked over subjects in race car simulation and race car engineering, and that is engineering for both performance and drivability. And where the motivation for this presentation came from today is I worked on a job for a customer, a very, very big one, and I've been signed up to NDAs to the wazoo about this job. But there were certain things that went down with this job that I just figured that were some real light bulb moments and some really big lessons were learned. So really, this is pretty much the crux of what we're going to be presenting today. So to set the scene, if we take a look at when we're talking about race engineering, performance engineering, anything that you do with making a car go fast, the two things that you're always going to be talking about are grip and handling. It's the two major things, whether you're at SCCA, whether you're at IndyCar, whether you're in NASCAR, whether you're in Formula One. They're the two things that you will always talk about. Now, most race car simulation packages focus exclusively on grip, and I got to admit, on this one, guilty as charged, Your Honor. And the reason that we've primarily focused on grip, almost at the expense of handling, and we're going to talk about this shortly, is that, look, we in automotive have typically done a pretty piss poor job of quantifying this. But today, we're really going to address that in spades. Now, as I said before, I worked in a job this year that really required not just the performance elements to be in place, but the handling elements in place. Because bottom line, what I was dealing with was a full-on fire-breathing monster. So what we're going to talk about today is the key lessons that got learned from that job in terms of tying together performance and handling. But I'm also going to take the opportunity to speak. I'm also going to take the opportunity to talk about some lessons that you really should be applying in simulation and some tips and tricks and traps for young players. So let's get started. So first things first, a quick community service announcement about who I am, what ChassisSim is. So pretty much you've got a large number of simulation toolboxes. So these vary from lap time simulation, shaker rig, track replay, and driver in the loop. Now, ChassisSim has been used in formulas as diverse as LMP1, P2, IndyCar, F2, NASCAR, V8 Supercars, DTM. And for those of you who are going to be tuning into the Time Attack presentation where at the conclusion of this, ChassisSim has also been used very heavily in Time Attack as well. Now, the thing that ChassisSim brings to the party is its ability to reverse engineer tire and aero models from race data. That is an absolute key capability, because when it comes to race engineering and performance simulation, look, pretty much everything that you can do on a race car, you can pretty much measure on a set of pads using a tape measure and a ruler. Now, look, if you want to get cute, you've got things like KNC rigs, you've got things like shaker rigs, but pretty much you can get to about 80 to 90% of the story, using a decent setup pad, set of rulers, tape measure, a couple of scales. Pretty easy. However, what ChassisSim brings to the party is to combine this and using the race data, to fill in the blanks of what you don't know. And vis-a-vis those two grey areas are invariably always going to be tires and aerodynamics. And ChassisSim has got that ability to help you fill in that blank, to fill in those blanks. Now, the thing about ChassisSim is at its core is a full fire breathing 21-state multi-body vehicle dynamic model. So what that means is the thing that makes ChassisSim unique is its transient simulation throughout all of its toolboxes. We are talking the track replay, the shaker rig, driver in the loop, and the lap time simulation. The code commonality across all of that, when you dig into the numerical engine, is about 95%. And honestly, it's more just to and those code differences are more just to customize it for what it actually has to do. So what that means, it can deal with situations like this. So what we've got here is that you've got so this is the lap time simulation. You've got speed, you've got steered angle, you've got throttle, and here are your front and your rear tire loads. Notice how those tire loads are bouncing around. What that means is that you're going over a bump. To quote a IndyCar colleague of mine, this takes ChassisSim well beyond the ability of just simply doing wings and gear ratios. It opens up so much more that you can do with it. And when it comes to transient lap time simulation, we were the first to market, and we are the industry standard. Now, in terms of what ChassisSim delivers, when you have done your job right, when you've gone through, you've measured the car properly, you've calibrated the data appropriately, you've gone through in systemized fashion and put it all together, this is the correlation you should be expecting. Now, actual is colored, simulated is black. So what we've got here is that you've got speed, throttle, front dampers, rear dampers, steered angle of the tire, lateral G, longitudinal G, front and rear roll. That, folks, is the end point of when you have done your job properly. And that, ladies and gentlemen, is the results of the lap time. And that, ladies and gentlemen, is the results of the lap time simulation. Now, to sort of set the scene for our discussion today, and this is a slide I presented last year, and I think, even though strictly speaking, it's not related to what we are going to talk about today, I think I really wanted to ram this home for completeness. So what does race car simulation tell you? So what we've got here is correlation between super speedway, speedway stuff of actual versus simulated. So again, actual is colored, simulated is black. So what we've got here is we've got speed, steered angle, front pitch, which is the average of the front dampers, and rear pitch, which is the average of the rear dampers, and we've got lateral G and longitudinal G. So we've got decent correlation except for the rear. Now, most people at this point take one look at the rear correlation, throw their toys out of the pram, and throw a temper tantrum. Now, what this is just showing, and this is where you've got to look at simulated data with slightly a bit of a different lens. What this is just showing you is there's a hole here in the aero map, and it's your job to chase down what that hole in the aero map is. And that really rams home the point that what a simulator is, it's a calculator. It's not a magic wand. And I really want to ram that point home, because one of my big bugbears in this business is that everyone's obsessed with the latest tweak, the latest magic wand. There's no, guess what? They don't exist. if you're serious about performance, it's about using tools like simulation, like CFD, which Ray Leto from Total Sim presented last year, as calculators to help you understand your race car. And I really want to ram that point in. And to be quite honest, if you're after magic wands, I can tell you right now, I actually don't want your business because quite frankly, you're going to be more trouble than what you're worth. So moving on. Okay, let's talk about the two main currencies of a race engineer. All car performance, it boils down to grip and it boils down to stability. And the following is a perfect case in point. This is the last time that Ayrton Senna crossed the start-finish line. This was Imola, May 1994. So what we've got here is the Williams FW16B versus the Benetton B194. Now, on paper, Ayrton Senna should have had a magic carpet ride to his fourth world title. It had the Williams had the engine of the field at that time, the Renault V10. It had the best aerodynamics on the grid that produced the most downforce, albeit, and there's going to be a but here, for a very, very narrow band of ride height, and it had clearly the greatest F1 driver of all time. But here's the thing: that car, that blue car there, had been designed for active suspension. What that meant is the aero only worked in a very, very narrow band of ride height. So in August 1993, the FIA, in their so-called infinite wisdom, decided to ban active suspension. So you had what was an active car all of a sudden being thrust into being a passive car. And so this was a car that had incredible Jekyll and Hyde handling. Indeed, Ayrton Senna's race engineer David Brown once said that for the first 3 races of the 94 season, the Williams wasn't on pole, Ayrton Senna was. Now, in the background, the car that was chasing him was the B194 driven by Michael Schumacher. Now, this car was, in terms of straight line speed, I think down something like 20k an hour on the Williams. However, from the ground up, this was designed as a passive car. It had not just great grip, but great handling, which allowed Michael Schumacher to compete on level terms with Ayrton Senna. And this really rams home the importance of what we're going to discuss today. Now, in order to talk about race car handling and how we quantify race car handling, we need to have a pretty serious chat about how we quantify this. Because make no mistake, when it comes to quantifying race car handling, we in motor racing do a pretty bad job of it, and OEM does a really piss poor job of it. And the reason is that we tend to throw out terms like understeer, oversteer. Yeah, she's loose, she's tight. We throw these terms around like frisbees. And here's the thing: what we're describing when we're talking about things like that, we're talking about the end result. But what we don't know is what actually gets us to that end result in the first place. And the thing that drives that end result is that moment arm between the center of the lateral forces and the center of gravity. It's put in aerospace parlance, this is called the static margin. And what the stability index does is the stability index basically takes this concept of the aerospace longitudinal static margin, applies it for automotive use, and non-dimensionalizes it by the vehicle wheelbase. That is the stability. That is the stability index, and that is ultimately the thing that's going to drive whether you've got understeer, whether you've got oversteer, and whether the nut behind the wheel can actually hang on to the car. This is the money shot here, right here. Now, I know for a number of you tuning in, you might be a little bit freaked out by it. In chapter 5 of my book, The Dynamics of the Race Car, I actually go into great depth as to why this is the case. But again, as we go through the presentation, you're going to see the evidence of this, so bear with me. Okay, so what do all these values mean? Less than 0, the car is stable. If you give it an input, it ain't going to swap ends on you. If it's equal to 0, if you give it an input, it's just going to keep on going. If it's greater than 0, this is when you give it an input and it's swapping ends. This is typically where the driver soils their racing overalls, comes back into pit lane, and starts referring to you in rather negative terms. Okay, so rough rule of thumb, the thing that sorts out the Lewis Hamiltons, the Max Verstappens, the Jimmy Johnsons, the Scott Dixons, your AJ points from your mere mortals is they can tolerate a car with very, very low values of stability index. They're the things that separate your superstars from driving Miss Daisy. Now, a rough rule of thumb, a good value of stability index is about -0.05 to -0.1. And rough rule of thumb too, you get the occasional excursion to about 0.1, but again, we'll talk about the significance of that shortly. Right, so quantifying this. Now, one of the things that we talk about in race car engineering is the lateral load transfer at the front. It's also called the magic number. And again, it's one of these things that tends to be thrown around, a little bit like frisbee. It first started to get used around about the mid-80s and really sort of took a life of its own in the mid-90s. Now, what the lateral load transfer means is the percentage of load transfer on the front axle. Now, if you plot that versus tire grip, you get a curve that looks like this. So typically, and this is for an F3 car, you've got about 20 to 21,000 newtons worth of force with a variation of about 1,000 newtons or so. So that's about a variation of about plus or minus 1,000 newtons. But where the real magic of the magic number comes in is how it varies the stability index. So as you can see up here, sure, we had a bit of variation, but not a lot. Here, all of a sudden, we've got really big changes in stability index. That's the thing that the driver is going to come back to you and start screaming blue murder or be really happy about. And that dance of tuning the stability index the driver can cope with and maximizing that grip, that's the dance that we dance as race engineers, performance engineers. That is the dance that we dance. And I often refer to this as the mechanical grip balance equation. Now, in terms of quantifying this and putting numbers to this, this is where we need to quantify our race tire. Now, that's beyond the scope of our discussion today. However, for those of you who are interested, I would refer you to the ChassisSim blog post, tire modeling from nothing. For those of you with a search engine, just search ChassisSim tire modeling from nothing. It will be the first result that comes up. Now, the real key to nailing this is the nail here is to quantify. We can quantify this, and the key to quantifying this is knowing that in any thermal condition, a tire can be nailed down in terms of the load at which it produces its peak force. So typically, you've got the initial coefficient of friction times your peak load divided by 2 and your peak load. Those two variables there really allow you to nail down the racing tire. Now, I could probably give a seminar in its own right about the significance of this, but let me give you the really, really quick elevator speech. This tells you so much about the soul of not just the racing tire, but where you go with setup. So let me give you an example of this. If the load that you're seeing on track is only about 50% of the load at which the tire is going to generate its peak grip, that is telling you you want low roll sensors, you want low pitch sensors or low values of anti-dive and anti-squat, you want stiff spring and bar rates and stiff damper rates. Why? You've got a tire that needs to be muscled to get it up to temperature. Conversely, if we've got if our peak tire loads on track are about 70% of the peak tire load where we generate our peak grip, as a rough rule of thumb, that is telling you high roll sensors, high pitch sensors or high values of anti-dive, anti-squat. And it's also telling you soft spring rates, soft damping rates, soft bar rates. Why? You've got a tire that needs a lover with a slow hand and needs to be treated very gently. But the thing about it is that little curve there allows you to fill in the blanks of this. This is why it is so very important. Now, what does that stability index look like through a corner? So what we've got here is an example of a Formula 3 car where we've got the base standard F3 car and we've moved the aero balance forward about 5%. The colored trace is the standard. The black trace is where we moved the aero balance forward by 5%. So this is the results of the lap time simulation And this is pretty much a high-speed sweeper where we just basically roll the car into the corner. So what we've got here is that you've got speed, so you've got a little bit of difference there. You've got steered angle. Now, obviously, because you've moved the aero balance 5%, you've got a little bit less steering lock, but not massively. We're going to talk about that. We'll talk about the significance of that in a little while. You've got minor difference in throttle application. You've got minor changes in terms of grip, but where you're going to see a big change is the stability index. So the standard was about minus 8.7%, moving the aero balance forward by 5%. That gives us a stability index of about minus 5%. That's the driver, because I guarantee you, you put in, you've got a baseline F3 car and you move the aero balance 5% forward, that's the thing the driver is going to come back to you and say, my word, that's a huge, huge, huge difference. And the thing that's driving it is that delta in the stability index. Now, the great thing is that we can actually incorporate this in ChassisSim. Now, the way that we do this is we basically have a setting in ChassisSim under the inertial properties where you've got driver stability index, we've got driver stability settings, and you fill in this stability index table versus speed. So what this is this is a corner multiplier. What happens is that ChassisSim figures out the maximum performance of the car without due regard for man, woman, child, or beast. And then what it then does is it looks up what the stability index was and looks at where it falls with this multiplier. So if you've got a car with a very low value of stability index that's going to be really twitchy that's going to be really twitchy at the mid corner, you can now take that into account with that multiplier here. Conversely, if you're dealing with a car that's understeering like a pig, it will also penalize that as well. And you can tune that to what the likes of what the proclivities of your driver. Now, in terms of what this looks like, in terms of your results. So what we've got here is I ran two simulations, one with an F3 car, the other one with a V8 supercar around around Queensland Raceway that's based in Queensland, Australia. The place itself is to be honest, the place itself is a bit of a dump, but it's a good little test circuit because you've got a bit of everything. So as you can see with the standard case with no stability index correction, we got our baseline, we've moved the aero balance forward by about 5%. That's dropped the lap time by about 0.1 of a second. The aero balance back by minus 5%. So the so the performance is going to be suffering, and all your various other bits and pieces. When we turned on the stability index correction, a totally different ball game emerges. So indeed, one of the great criticisms that's often leveled at lap time simulation is that as you start moving the aero balance, the aero balance forward, what happens is the lap times just get better and better and better. But the problem now, the thing about it is, yes, the car is quicker, but the problem is it's becoming more and more it's becoming more and more undrivable. This is where the drivability starts to kick in. And with the stability index correction on, you can see with the aero balance at plus 5%, the lap times are penalized quite heavily. Why? It's a lot more oversteering, and we saw that through the stability index. Ditto with the aero balance at minus 5%. Again, a further penalty. We've lost grip, but we've also lost handling as well, so you've got a double whammy there. Ditto with the rear bar being moved from 1,200 newtons per millimeter to 600 newtons per millimeter. You can see you've now got a 0.3 of the second penalty. And with the rear spring going from 900 pounds to 800 pounds, you've got a little bit of a penalty, but not a lot because it's a much minor change. Now, when we did that to the supercar, what you can see is that number one, you had relatively smaller changes. Again, favoring oversteer, it got a little bit quicker. Again, that track does like a car that can point around. However, once we turn on the stability index, again, a much different picture. So anything that would promote oversteer, and that was due to the nature of the stability index map we used, again, penalizes the car a lot more. So this now opens a much wider window of parameters that you can now put in. So now you've actually got a very firm basis of which you can predict race car handling with. So that's part one of the story. Part two of the story is enter ChassisSim driver in the loop. And really, we're now getting to the crux of what motivated this presentation in the first place. So as I said before, I was working on a job this year that was a car that was a fire-breathing monster. Unfortunately, I have to be extremely tight-lipped about I have to be extremely tight-lipped about what this car is, because I'm signed up to NDAs up to the wazoo about this. However, what was happening was that because this car had so much downforce and so much grunt, I basically took what I thought was a good baseline, and it was starting to push. When I was testing this around Eastern Creek and ChassisSim driver in the loop, I was getting into turn one that should be, for a high downforce car, you just turn in, hang on the throttle, and you don't even think about it. Every time I was turning in, the car was flopping in. Why? What was happening? What was happening is that all of a sudden we were starting to push into very unstable behavior of the car. And let me leave the punchline for this momentarily with what I'm about to show you. Okay, so what we did was I took a look at looking at the lessons I learned from that job, and I said, okay, can I get repeatability here? Is there a common trend here? So what I did was I took the LMP2 Plus car that was the basis of last year's ChassisSim online race engineering competition. And I knew that car had really borderline stability. Indeed, when we did the driver in the loop section for that, it was the one thing that the driver really did struggle with. So what I did, I just figured, okay, let's move the aero balance back about 5%. So as we can see here, the color is the baseline. The black is moving the aero balance back about 5%. So what we've got here is you've got wheel speed, you've got steered angle, and again, we've got slightly more steering lock for the black for the aero balance being moved back by about 5%. And a little bit less lateral G. But if we take a look at the stability index, which is this last trace down here, going through turn one, the car is absolutely borderline stable. And I mean borderline stable. It's going to basically go at you pretty much almost at will. But with the aero balance of 5%, we've now moved the static margin back from about -5 to 0 to -10 to about -10 to -5. And I figured, okay, that's interesting. Let's park that for the time being. Then what I did was I said, okay, can I get repeatability with the F3 car? So what I did was I took the standard ChassisSim template, ran it at Eastern Creek, and ran it across driver in the loop. So the baseline, which is colored, was about a stability index of about -3.6%. So what I then did is say, okay, what can I do to move this so the stability index becomes 0? So I basically just kept moving the aero balance forward. And I got an aero balance of about 10%. The car is now, stability index is now 0. And I figured, okay, now we've got these two data points. Let's run this in ChassisSim driver in the loop. Now, my apologies in advance if the videos here are a little bit delayed. There's also, and I've also done a YouTube tutorial on this. So if it's a little bit delayed here, you can chase up that YouTube tutorial on the ChassisSim YouTube channel. So let's take a look at the LMP2 baseline. And I'm not going to go full screen so that we don't get that much of a screen delay. So going into turn one, this is with our LMP2 baseline with our borderline. So as you can see, it's a little twitchy going into turn one. So a little twitchy. Now we're going to go into the exit. Now I've got a bit of a tank slapper happening. Going in and whoa, go tank slapper, all sorts of dramas. Let's now take a look at that aero balance being moved backwards 5% on that LMP2 Plus car and see what we're dealing with. So coming into turn one, coming in a lot more settled, no twitching, no nothing. We're now going to go into turn two at Eastern Creek, solid as a rock, turning in, go. Not doing anything nasty on you. That's just me being an idiot, getting on the throttle too early. But again, all solid, nothing particularly outrageous. Let's now take a look at the F3 car. So here's our baseline. So coming into turn 1, we whack it in, no huge dramas, pretty stable, etc., etc. Going into ditto under brakes into turn 2. So pretty much pretty much all run-of-the-mill stuff. Let's now have a look at when we've moved the aero balance forward by about 10%. So coming into turn 1 and going in, and we've got the tank slapper happening. So this is basically when the race car driver basically stalls themselves. And ditto, not good at not good at all. Actually, around here, this has been taking a look at the video. This is now when the speed really cranks on, and whoa! That's basically fresh laundry, but that's basically fresh laundry material. However, here's the nail. Here's the nail, ladies and gents. The nail here is we were able to use the stability index from the lap time simulation to predict what was going to happen with driver in the loop, vis-a-vis that point where we were going to go between something that we could hang on to and not hang on to. So we take a look at that bottom trace here. We've got minus 3.6% for the F3 car. When we moved our aero balance forward by 10%, it was going to be really marginal. And we saw that in the video. Going back to the P2 car, again, you've got the colored trace, which is the P2 car as standard on the bottom here with the stability index. So here it's really, really marginal. And with the aero balance now moved back by about 5%, all of a sudden we can hang on to it. And we've been able to use the lap time simulation to do this. And this is really key for that job, because when I just went through, so I just threw some stuff at it at random just to see, hang on, what's going on? But then when I went back and looked at the stability index channel, you could see once it was going into turn 1, the stability index was just going off the scale. And that's why I couldn't hang on to it. And that, folks, is how you can use your lap time simulation to really help you nail down what's going to happen with your race car handling. Now, in terms of some rough rules of thumb. Now, a lot of this is going to be dependent on engine power, and that's down to 2 reasons. Number one, the limitations of the stability index calculation in ChassisSim as it is right now. I do have something in there. I have formulated stability index for mixed, for both longitudinal and lateral applications. I just haven't had the time to implement it. So here are some rough rules of thumb of where you need to be looking in terms of the stability index when it comes to driver training in when it comes to tuning for handling. So if your engine power is about 170 kilowatts at the wheels, or about 220 horse, give or take, your superstar will be able to cope with about -3 to -4%. Your average driver -6 to -8%. Your bad driver -12 to -16%. Once you move into an engine power of about 400 kilowatts or so at the rear wheels, or about 500 or so horse, you're looking about your superstar will cope with about -5 to -7%. Your average driver will cope with about -10 to -12%. Your bad driver is about -16%, and your engine power over 600 when you're talking 600 kilowatts or about 750 horses, your superstar will cope with about -8 to -10%. Your average driver is about -12 to -14%, and your bad driver is about -4%. Again, these are some rules of thumb, but the real takeaway here is that you can now use the lap time simulation and know and look at the stability index values and know that's going to give you great confidence to know that's going to translate to what you see in the real world. Because as we saw with those 2 videos, you could see a really clear correlation between what you were doing with the stability index and what you were doing with driver in the loop, and that in your ability to be able to hang on to the car. So that's something that's incredibly powerful. So that being said, let's now talk about the simulation approach now that we've got this to hand. So the first thing to do with the simulation approach is step 1. is you sort out your mechanical and aero setup. Now, the great thing about the lap time simulation is it'll allow you to sort out things like your aero, springs, bump rubbers, ride heights, gear ratios. That stuff pops out really quickly. Once you know that, you can then use a little Excel sheet combining a very simple tire model to allow you to tune in the lateral load transfer distributions that you're after, and in particular, that balance between handling and that balance between grip. It's a very, very powerful tool. And again, it's in that link, ChassisSim tire modeling from nothing. Once you're done with that, you then get on to sorting your dampers. You start with a quarter car damper model. Why do you start with a quarter car damper model? It's simple. It allows you to be numerous about what you're doing with the dampers. And that's where, and once you've got to base it up, that's when the ChassisSim Shaker Rig Toolbox becomes your best friend, because it's such a powerful tool to help you sort through your damping options. And this is something that I speak about at length on the ChassisSim YouTube channel. I also talk about it at length in the ChassisSim boot camps. Once you've done, you're done with that, you then go through and look at your lap time simulation and driver in the loop. And in order to do that, you really have to understand the race engineering process. So it starts with your driver feedback. You then take a look at what the data has told you. You then take a look at your lap time simulation, and then you move on to driver in the loop. Bottom line is that the lap time simulation helps you sort through the options. The driver in the loop will determine if those options are drivable. And indeed, one of the things that I really learned in the ChassisSim driver in the loop development is one of the things I found really beneficial is that when I would be giving changes for driver in the loop, I would actually be standing next to the driver, just seeing what they were doing. And that was actually a really great educational experience for me, because it gave you red flags to go through when I looked at the data so I could make sense about what was going on. Okay, simulation traps for young players and some tips and tricks. Okay, first things first, setup sweeping. Use this with extreme caution. Now, don't get me wrong, setup sweeping has its place, but the big trap that I see young engineers fall into, and I see the big end of town, like F1, NASCAR, IndyCar, and factory LMP1 fall into, is that they'll just use they'll over-rely on setup sweeping. Here's the thing, you've got to stick with the parameters that you've modeled, and you always stick to within plus or minus 30% of your base setup. Anything beyond that, you're just guessing. So really keep that in mind. Now, the other thing too, DIL. Okay, a couple of disclaimers here, because the problem with driver in the loop rigs is they've become the next magic bullet. But there's really some key disclaimers here. Number one, this ain't going to be for everybody. In order to make use of driver in the loop and to make use of this properly, you've got to possess what I call the RC Aviation gene. These are the ability to take visual cues, figure out what the plant's doing in your head, and then figure out what to do with the driver controls. And make no mistake, not every race car driver you'll deal with will have that ability. And indeed, I would actually have to say that the fool's paradise that everyone tried to chase with driver in the loop was thinking this could be for everyone. It's not going to be for everyone. And to presuppose this is going to be for everyone is a little bit like thinking that denial is a river in Egypt. The other thing too about DIL is it's not a magic bullet. And indeed, one of the great fall downs of driver in the loop is everyone thinking this is a magic bullet. And make no mistake, while it's a great tool, it's not a magic one. And for the love of God, do not fall into the President Camacho trap. And what I mean by the President Camacho trap is this is a screenshot of the movie Idiocracy that translates what happens in 500 years' time when all the smart people stop reproducing and all the idiots keep reproducing. And so an average army private wakes up 500 years later and he finds out that he's the smartest man in the world. And he wakes up into a world where for decades everyone has been spraying crops with Gatorade. And they wonder why it's not growing anymore. And President Camacho gets in front of everybody and say, "We got this guy not short. He's the smartest man alive." He's going to fix the plants. He's going to fix the economy. He's going to do it all in 1 week. If that is your attitude with driver in the loop, you're wasting your money. It just simply is not going to, you will be doomed to perpetual disappointment. The other thing to really flag here too is that simulated changes will always be smaller than actual data. Reason one is the nature of the tire model. Reason two, a simulator, ChassisSim in particular, is the Terminator. It knows exactly where the grip is. It does not know pity. It does not know fear. And it absolutely will not stop until it's achieved maximum grip. So consequently, when you go through and take a look at simulated data, you'll have very small changes in steer angle. You'll have very, very small changes in throttle. But where the changes show up is in cornering speeds. And that is a key difference between looking at simulated and actual data. Now, in terms of the setup parameters you need to be working with, and I think this is actually, we in the race car simulation community have been very, very guilty of this, because typically what we do is that we give you great correlation that I refer to as simulator porn. We then go through and everyone gets really focused about correlation, and then they go off and use the simulator, plug in all sorts of silly numbers in it, and wondered why the results don't tally up on track. Okay, so here's some rough rules of thumb when you're getting started. Spring rates are going to go about plus or minus 20% of the base setup. You keep damping ratios to known values of the base setup. Why? Because if you go beyond that, you're going beyond the area that you have a model. And number two, if you get out of that window, the tire temperature effects start to become very, very radically different. And even when you've got tire temperature modeling turned on, you can still sort of fall into this trap. That being said, you can lean on your camber changes, stick your bars to within plus or minus 30%, your geometry is about plus or minus 20%. Also, to start from a well-known model and modify to suit. You do not get any brownie points for showing how intellectually brilliant you are. Lastly, some conclusions and food for thought before I turn it over to Q&A. First things first, and the real nail of today is what you see in the lap time simulation for stability index will be reflected in driver in the loop. Now, sure, they're going to bounce around with the engine power that you run, but the real nail here is that you can now be very, very deliberate about how you specify race car handling. And that is so key, because so much of what we do in this business is like, oh yeah, I feel it did that. I feel it did that. That's great. If you want to feel that, go to a touchy-feely church, hold hands and sing Kumbaya. But what we're talking about now is what we've discussed with the stability index. Its correlation to what's done to driver in the loop. It now gives you the ability to engineer the car as opposed to guessing, and that, folks, is an absolute game changer. So at that point, let me conclude the formal part of the presentation. And Joe, I'll turn it over to you for the Q&A.
Excellent, excellent. Thank you very much. And can you read me?
I've got you loud and clear. Got you loud and clear.
All right, good. I'm not hearing myself back to myself. So if anybody out there has a question, I find it to be very interesting that you can go through this process. And there was so much that you said, Danny, that you're taking something that is kind of an unknown and trying your best to quantify it in the software so that people can at least test, right? They can at least figure out. Now, much of it is over my head, but that is why we have got the Q&A session for Danny. Danny, you talked about engine power, though. How does this software affect that? You know what I mean? Like,
okay, so basically, what you're seeing there, engine power is what you're seeing there is the net result of the fact that, particularly for rear-wheel drive, is that with engine power is that you're asking the rear tires to both corner and do traction do corner and traction at the same time. And because of the fact that you've got basically pretty much your available grip is pretty much a traction circle. So, if you're trying to ask the tire to do both ridiculous amounts of traction and cornering at the same time, it's not going to work, which is why with those values of the stability index, you actually shifted them backwards with increasing level of engine power, because you needed to have, the tire actually needed to have excess grip so that when the driver gets on the happy pedal, he doesn't actually, the car is going to swap ends. It's a fundamental limitation of the tire.
How much time should be spent using the software in relationship to track time or?
Right, great question. Great question. So typically, this is where I go through. So pre-event, what I will do is I'll go through, do my vehicle modeling. And make no mistake, with your vehicle modeling, you're going to need about 3 or 4 bites of the cherry, or 3 or 4 different circuits to get it right, because you need to populate the tire model from different circuits. So typically what I do is that pre-event simulation is I'll go through, I'll make sure that I've got my correlation all squared away. Now, it doesn't have to be absolutely exact. And I talk about that in one of the ChassisSim YouTube channels in terms of how you look at simulated data. But once you've got that done, that forms your frame of reference. So that when you go to a test, when you go to an event, you're already pre-prepared. So you've got your test plan of stuff you wanted to test. You've got that whittled down. Once you've whittled down, you go to the track, you go through, sort through the data, you do your business on track as is. Now, if you've got really good computing resources and you've got a dedicated performance engineer, yes, they can use simulation if you need to ask some very, very quick questions. For example, I had an IndyCar customer whose performance engineer would actually be feeding stuff from ChassisSim to the race engineer in real time. But typically, this is where you're focusing on the race engineering of the car. You're looking at the data, you're correlating that against what you're doing. Once you're done with that and the session is done, you look through the data, you debrief with the driver. That's when you crank out the simulator to figure out, okay, is there anything that we missed here? Is there anything that's not adding up? That's when the simulator comes back to it at the track. I mean, if you've done your job really, really well, typically what tends to happen is the simulator tends to stay in the background at the track. That being said, it's also a great teaching tool for the driver as well.
All right, here's a question from Deanne. Is the $5 per online simulation, what would you recommend for amateurs?
Oh, absolutely. That is why that online simulation was created in the first place. It was created as a very, very affordable way to allow club racers, SCCA racers to access a tool like ChassisSim without breaking the bank. And typically we've got a number of options. If you're really, really technically literate, I mean, typically you just buy the simulations. And typically on your first simulation, when you buy your first simulations, like I'll typically throw you about 100 or so, 150 or so cents so that you can get up to speed. And typically for an event, you're typically going to be talking about 20 to 30 cents on the lap time simulation, another 20 to 30 cents on driver in the loop. That is so that basically is that situation. So so typically you'll be spending about $125 Oz to $250 Oz per event. And so that regards, I think for your SCCA runners, your amateurs, this is something that I highlight. The online simulation is your natural price point.
And I think that's something we need to spend a little time on. Like, all right, people understand that it's a useful tool, accessing the tool, getting assistance, accessing the tool, and learning to work with it. How do you handle all of that? And for people,
funny you should ask. There are multiple resources we've got to handle that. Number one is the ChassisSim YouTube channel. There are 120 tutorials there of me talking about all aspects of vehicle dynamics, all aspects of ChassisSim, etc., etc. So that's step one. Step two is the ChassisSim boot camps. So I run those twice a year, where I actually walk you through a work example about how you go about and walk you through the ChassisSim workflow. And typically day one is I'm working you through the ChassisSim process. Day two is that you're working on ChassisSim with myself or my colleagues, looking over your shoulder, making sure you're not doing anything silly.
Got it. Got it. And so for people out there who are interested, the best way to go to you and to begin the journey is to go to the website, ChassisSim.com.
Correct.
Excellent. Excellent. Now, I notice you do some modeling for Formula E. I wonder, electric power versus combustion. Does that change the simulation?
Not really. Look, the thing about it is, I mean, look, here's the thing about electric. Look, the number one, the huge difference between when you go electric racing and you go internal combustion is that with electric racing, because your energy densities are so marginal, you spend an awful lot of time talking about those compromises between coast, regen, between coast, regen, et cetera. The other thing too is that because with electric engines, because the torque is so instant, you will play around with things like the torque maps, so the driver, so the driver doesn't freak out. But when you're talking about engineering for max performance, whether we're talking the Neo or the Nürburgring or the Volkswagen IDR Pikes Peak, there's an awful lot of that when you're focusing on max performance. The performance is virtually, the process between internal combustion versus electric is virtually identical.
Very interesting. Very interesting. I see Francisque and Judy have joined us once again. Ladies and gentlemen, I am way more educated than I was 50 minutes ago about chassis dynamics, certainly, and how to solve problems, thanks to Danny. I know our audience is as well. Danny, thank you so much. That was an excellent presentation.
No worries, guys. Not a problem. My pleasure. And guys, great. And Joe, Francisque, Judy, really great to see you guys again. I hope you have a fantastic week. Unfortunately, I have to bail because I'm getting hammered here on multiple fronts. But one final parting word, guys, for those of you who are tuned in. Got any questions at all, look, email us at info@chassissim.com. The chat window, look, don't bother with the chat window terribly much. I mean, that's just more there for general punters who just, doing some casual fishing. But anyone who's tuned into this presentation, shoot me an email at info@chassissim.com if you're interested, and we can get you all sorted. And guys, you have a fantastic rest of the week, and really enjoy next presentation on time attack. It's probably my favorite formula to work in.
The concept for EPARTRADE is basically, in my opinion, there's a big hole in the internet. So the internet started many years ago, but there's never been an online business community for racers on the World Wide Web. The need for EPARTRADE is actually quite obvious. Basically, people in the business of auto racing need a place online to hang out and get their problems solved.
It's extremely simple for a buyer or for a supplier to interact on the platform. The first thing you need to do is sign in, which is free. And the second thing is, when you see a product that you're interested in, all you need to do is click on request more information. If it's a company, you click on request more information, and then from there, it is forwarded directly to the buyer or to the supplier.
You can go to epartrade.com, you become part of a community of businesses in racing, and it makes sourcing products much easier than just on the internet or using Google.
At EPARTRADE, there is no e-commerce. It's literally a connection just like at a trade show. So now, any time of the year, a buyer could reach out to a supplier through an email.
More than that, it's a place to go just to keep current every day. So it's a good place to start your workday in your racing business or in your offices of your professional race team. And you know you're current when it comes to new technology, industry news, technical papers, technical videos, all of that and more. We're not looking for a million hits per day. All we want is people who are really the volume buyers of racing products in the racing industry to be part of the little world of EPARTRADE. We have racing businesses participating from around the world. So you get suppliers from around the world, you get buyers from around the world.
EPARTRADE really eliminates having to travel, closing down your shop. Now you have a place to showcase globally your racing product and technology.
There are two types of people, racers and everyone else. Racer Magazine is for those who believe that racing is a way of life. Racer embodies the excellence that defines a sport driven by passion, courage, and ingenuity. Get 1 year of both Racer's print and digital edition for only $39 with instant access to our entire digital issue archive. Subscribe now at info.racer.com.